heavier one would fall faster. Of course, given air resistance, it would, but using cannonballs, they were dense enough that air resistance had a small effect. In fact, Galileo was a really good observer of nature. And he did note when he had other people drop it for him that the two balls did not arrive at exactly the same time. There was a definite thump thump and a time between them. And Galileo's critics noticed that too and said, no, but the larger one did hit first. But Galileo said that, Aristotle would say that the 10 times heavier one would arrive 10 times sooner, and it didn't. So there was slightly different. Yeah, and so you line up the balls by their bottom if you want to do the timing about when they hit the surface. And by putting them on a board and withdrawing the board really quickly, you can do a pretty good job of dropping them together. Now, the actual experiment was done by Simon Stephen Jan Cornets de Groot. I immediately thought of, my name is Groot, in 1586. He did it before Galileo. And the new church right here in the photo is the one he did it from. And he did drop 2 lead balls, one 10 times the mass of the other, and he dropped them 10 meters. If you're the student on the ground or standing near the ground when they come down, those lead balls are really going to hurt if they come down 10 meters. So it was known in Galileo's time what would happen if you actually did the experiment. So this is the beginning of experimental science. Yeah, so it turns out, Baragon, that the air resistance goes like the cross-sectional area, and the small one does have a smaller cross-sectional area. But the force of gravity on it, which is balanced by the air resistance, goes like the mass of the ball. And the mass goes like the cube of the radius. And so the bigger one, the ratio of the mass to the air resistance, the r cubed over r, the large one wins if it's a solid ball. Yeah. Galileo was a quantitative, even though Galileo was the one who observed the motion of pendulums in a church, and noted that the period of a pendulum was independent of the amplitude of the pendulum, and that eventually became the basis for clocks. He didn't really have a good clock when he was doing his experiments, but his father, the senior Galileo, was a famous musician. So Galileo grew up in a home full of music. So he used musical timing. And in this experiment, this is actually in a museum in Florence. And this really is Galileo's inclined plane. Look at the beautiful workmanship in the wood on this inclined plane. And the things that are on it are bells. So he would roll a ball down from the top here, and it'd hit the first bell, and then the second bell, and the third bell. And he would then listen for, he'd place the different bells so that they rang at a constant rhythm. Bing, 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 bing. In order to do that, if the distance from the start to the first bell was 1 unit, the distance to the next one added 3 more units, and the distance to the next one was 5, and then the distance to the next one is 7. And Galileo knew his mathematics so well that he knew when you added together odd numbers, start with 1, 1 plus 3 is 4, 1 plus 3 is 4, and 4 is a square, it's the square of 2. And plus 5, when you added that to 4, you got 9. And the square of 3 is 9. So he knew that the law for how things fell was that the distance that they traveled was proportional to the time squared. He didn't know the 1/2 yet, and he didn't know the g yet, but he actually, by his actual observations, he knew this law of falling objects. At the Exploratorium, we have something called the gravity-powered calculator. And you can put balls at different positions along this inclined plane, and they roll down the inclined plane and get launched off the end here at the bottom, and they fall down and they hit metal rods, musical rods down here at the bottom. And if you place them, so the first one goes a distance of 1, and the next one goes a total distance of 4, and then 9, and then 16, they hit the bars in the same musical rhythm that Galileo had. Bing, 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 bing. So we let you, and the way we release the balls all at the same time is that they're held in place by magnets, and you flip a lever and all the magnets move away. So we get away with the how do you drop everything at once problem. Now, there was a Jesuit priest, and the church was not happy with Galileo refuting Aristotle. A lot of the churchmen of the time studied Aristotle and really believed Aristotle was right. But so Giovanni Riccioli decided to actually do measurements, not with the inclined plane, but by actually dropping a ball from this tower, Asinelli Tower in Bologna. And he was a great experimenter. In order to time things, he wanted to make a pendulum. And the one thing he knew was that there are 86,400 seconds in a day. So he tried to make a pendulum that would swing back and forth in 1 second. So he did that. He made a pendulum. And then he got 3 of his Jesuit priest friends, and he started the pendulum at noon as the sun crossed the southern part of the sky, precisely behind a line, one day, and they counted until the sun came back to the same position in the sky the next day. And his number did not end up being 86,400. So he knew the pendulum was the wrong length. So he adjusted the pendulum, and they did it again. For a whole day and night, they counted every swing of this pendulum, 4 of them, and didn't get 86,400. So he changed the length of the pendulum again, and then again. And he's never got the exact 86,400. But finally, his 3 friends said essentially, no more Riccioli. Well, that's good enough. But we now know he was really close to having a 1-second pendulum. He told his, oops, your voice is breaking up. Uh-oh. Hope not. Okay. So, but the time of falling object, 1-second pendulums weren't enough. So what Riccioli did was he made a pendulum that went 6 times a second. Now that's really fast. I'm going to try. I have a clicking pendulum here that goes 6 times a second. Let's see if we can pick that up on this machine. Could you hear that? That was 6 times a second. And he and his Jesuit friends managed to count the fall of these balls to 1/6 of a second. I'm as impressed. Yeah. So he actually measured the fall in Roman feet, and we would have no idea what a Roman foot was, except he included this diagram in his science report, and the tower still exists, so we can actually back calculate and find out what a Roman foot was. And at the end of his investigation, he found out that Galileo was right. And I think this is one of the first examples of a really good science paper. Here we are in 1651, and we can go back and know that he got the seconds right and know what distance he used, because he used this tower, which is still in existence, and he put a diagram in his paper. So he was trying to prove Galileo wrong, and he ended up proving him right. That's the essence of science. You can have a wrong idea, but you do the experiment, and you get the right answer. Well, then we jump ahead. Galileo dies, and in the same year, Newton is born. And Newton also studied falling things. And of course, you all have heard about Newton and his apple. So here we are, 1666, Newton's apple. And but you ever wonder what that story about Newton's apple really was all about? Well, in this picture, notice the moon also appears. So Newton knew that the apple fell, we call it in our modern units, 10 meters per second square, is the fall of the apple at the surface of the Earth. And the surface of the Earth is 1 Earth radius from the center of the Earth. The moon, he knew, was 60 times further away from the center of the Earth than the apple. It was 60 Earth radii away. And he calculated during the course of a month, in 1 month the moon goes around in its orbit once, and he knew that to move in a circular orbit you have to be falling towards the Earth all the time, and he knew the fall rate. He calculated it. It was 3 times 10 to the minus third meters per second squared. And that's 1/60 squared of the fall rate at the surface of the Earth. And 1/60 squared, that told him that the gravity that caused the fall of the moon and the fall of the apple decreased like the square of the distance. And he got this equation down here. Well, that's our modern version of it. There's a constant, the universal gravitational constant, times the mass of the Earth, divided by the distance between the center of the Earth and the object squared, and that gives you the acceleration. And he put this in his book. Newton published a book with these numbers in it. And the printer, the one who was typesetting it, remember, he's typesetting it backwards, read it and said, "Oh, Mr. Newton, you made a mistake. The distance to the moon is wrong." And it turned out that in Newton's time, the accepted distance to the moon was not the distance that Newton used. But in the end, Newton was right. He got the right distance to the moon. So this was probably not the best example of science. Also, other scientists have done this in time and said, "Oh well, that data must be wrong," and I'm going to just use the data that corresponds to my theory. And not all of them has been as lucky as Newton, and realized that the data itself was wrong. Well, now the problem was nobody knew what G was, this capital G. What is the value of G? And so 100 years after Newton, Cavendish just actually measured G. And he did it in this apparatus. He had a huge lead ball. And if you go to Germany, to the Deutsches Museum, they actually have one of Cavendish's lead balls. And he had a smaller lead ball here that was near it, which was hanging from what's called a torsion pendulum. You can't hardly even see the string here. In fact, I'll show you a diagram that'll help you understand this better. So he had these 2 giant lead balls and 2 small lead balls in red hanging from a torsion wire. And when he moved the big balls next to the small balls, the gravitational force between the large lead ball and the small one pulled it over to the side. So he could actually measure the gravity force by these lead spheres. Yeah, I really, if you're in Germany, seek out the Deutsches Museum. You can go and see the actual tools used in the most famous science experiments. For me, that was just a joy. So now we know, and there are many ways to measure this, so these numbers are approximate, that the gravity force is 10 to the 38th power times weaker than the strong nuclear force. It's 10 to the 36 times weaker than the electromagnetic force, and 10 to the 29th times weaker than the weak nuclear force. So the thing is that gravity drops off like the inverse square of the distance, and the nuclear force drops pretty much to 0 very quickly at any distance over 10 to the minus 15th meters. So over long distances, you don't have to worry about the nuclear force directly affecting you. And the electromagnetic force, although it's also inverse square and reaches really long distances, it comes in 2 varieties. It has plus charges and minus charges, and they usually occur in an object like me in equal numbers, so that I'm not charged. And so this cancels the long-range effects of the electromagnetic force because almost all objects are neutral. But as far as we know, mass has only one sign. There's only positive mass. Although, scientists like to check things. So one of the things they're checking at one of the things I was that we're checking is that at CERN they make anti-hydrogen. They use the particle accelerator to make anti-protons, and they have a second particle accelerator that makes anti-electrons, and they combine them. They stop them. That's the tricky bit. They make these antiprotons traveling near the speed of light, and they have to stop them and then combine them with anti-electrons. They make anti-hydrogen, and then they release the anti-hydrogen and see, does it fall or does it rise? And they've done some preliminary work, and it looks like anti-hydrogen falls just as they'd expect. But they still want to continue the experiment for a few more times to before they publish. But I'm really glad they're checking. Does antimatter have anti-mass? My bet is that antimatter has positive mass, but we're doing the experiment. So you can make antineutrons in these collisions, but the antiprotons and the antielectrons are the ones we really are experimenting with at the moment. I'm cleaning up my chat box so I can actually see when people type things. Like Chantal just sent me a message and I missed it because it was lost in a flurry of other messages. All right. Yeah, we are really, really neutral. When you rub a balloon in your hair and charge up that balloon so it sticks to a wall, there may be 10 to the 10th extra electrons on that balloon. 10 billion sounds like a lot, but when you realize that there are more than 10 to the 23rd atoms in there, the fraction of 10 to the 23rd made up by 10 to the 10th is nothing. So it's really well balanced pretty much all the time. Okay, so now we've done much better measurements of the universal gravitational constant than Cavendish. So here it is, 6.67408 times 10 to the minus 11th Newton meters squared per kilogram squared, plus or minus 0.00031. Now that may sound like we know it really well, but this is one of the least accurately known fundamental physical constants. It's really hard to measure. Now, you may not know this about physicists, but physicists argue over things a lot. In fact, some physicists define what is weight as compared to mass. We all agree what mass is, but weight is what's measured by a scale, is one definition of what weight is. And by the way, this image on the left here was taken in the Splo Museum in the early days of Second Life. And I actually do have a scale there that will give you your weight in Second Life. And other physicists define weight as the force of gravity on a mass. And you say, well, isn't that the same? Well, let's take a look at in free fall in the International Space Station. So in the International Space Station, if you stand on a scale, it doesn't measure anything at all. You just float there. You're in free fall. And so in that point of view, your weight on the International Space Station is zero. You are weightless. So you might hear that those astronauts are weightless, and that's the definition of our group of physicists who define weight as what's measured on a scale. The other physicists find your weight on the International Space Station using the equation for gravity for weight, the universal gravitational constant, the mass of the Earth, your mass divided by the distance between you and the center of the Earth squared. The Earth's radius is 6,400 kilometers. The ISS is 400 kilometers above that. And if you take 400 over 6,400, you're 6% further away from the center of the Earth in the ISS than you are on Earth. Since the weight goes like the inverse r squared, this means that your weight on the International Space Station, by this definition, is 12% less than your weight on Earth. And to the scientists that define that as the weight, you're not weightless. You're in free fall. So, but this shows you how astronaut mass is actually measured. They put the astronaut in a little chair that slides left and right and left and right and measure the acceleration of the astronaut. And so they can make sure whether they're losing weight or not. So it turns out there are many different kinds of mass, actually. There's the mass up here, which is capital M, which is the mass of the Earth that makes the gravitational force. There's the mass of the object, small m, that feels the gravitational force. And then there's the other classic equation we started with, F equals ma. And that mass there is called the inertial mass. And it's the mass that resists acceleration by any force, including a spring. And the amazing thing that as far as we can measure, gravitational mass and inertial mass are identical. And the mass that makes gravity and the mass that feels gravity is identical. Here's something. You want to think of yourself as a Superman? Get this. The Earth, with its giant mass, is pulling on you with a force. Well, you, with your tiny mass, are pulling on the Earth with the same force. This is action and reaction. Newton knew this. And so the force of the Earth on you and the force of you on the Earth are equal and opposite. You pull on the entire Earth. Now, the thing is, if you jump off a building, you have a small mass, so your acceleration is the force of the Earth on you over your mass, which is small mass of you. So you accelerate down fast. The Earth, on the other hand, accelerates up to meet you, but it's got a humongous mass, so it accelerates up towards you really slowly. So as a result, really, you do plummet down to the Earth. That's right. So Barragan says, when you pick up a rock, the electromagnetic forces inside of your muscles are pulling up more strongly than every one of the atoms in the entire Earth is pulling down with gravity. So now let's take a look at some of the planets. On Earth, the acceleration of gravity is 1g, and I have a weight of 150 pounds. If I go to the moon, acceleration is a sixth of a g, and I would have a weight of 25 pounds. I'd still have my mass. I'd still have the same mass of 70 kilograms or so. So it's just as hard to get me started moving on the moon as it is on Earth. But the moon itself is pulling me down much less. Mars, 0.376 g, it's more 56 pounds if I stood on a scale, a bathroom scale on Mars. And Jupiter has no solid surface, as far as we can tell. But if you're in a balloon floating in Jupiter's atmosphere at the top of the clouds, there's like 2.5 times stronger gravity than on Earth. You'd actually be pulled down towards the floor of that balloon with a 375-pound pull. It's like carrying someone on your shoulders all the time. So might be a problem. Yeah, so Charlize, I'll get to black hole in a bit, and we'll find that you're right. The force diverges. Oops. So for a little break here, I have a little trouble showing videos in Second Life at the moment. So in front of me there is a blue box, and if you touch this blue box, it should give you a note card, and on that note card there are a list of wonderful videos that you can watch to accompany this lecture. And in the first video, it's astronauts on the moon dropping a hammer and a feather, the classic experiment. And the hammer and the feather hit the surface of the moon at the same time. It's in a vacuum, and without air resistance, feathers and hammers all accelerate at the same rate. Yeah, so the terminal velocity operates on the same principle anywhere. If you know the density of the atmosphere where the air resistance resists the fall and the gravitational force, you can find the terminal velocity. On the moon, there is no atmosphere, so there is no terminal velocity. And actually, you might not know that I think it was Gene Cernan, when he released that feather in the test experiments, the feather stuck to his glove. And so he was very happy when he actually opened his hand and the feather dropped. So, you know, that stickiness bit is a problem. In the second of the videos, it's 4 minutes, don't watch it now. They actually go to the world's biggest vacuum chamber, and it's 10 meters high, and they have a bowling ball and a feather, and they release them at the same time from the top of the vacuum chamber and then give you a close-up view of the bowling ball and the feather hitting the floor of the chamber at the same time. This chamber is used to test very large satellites and see how they work in the vacuum of space. And it's great to watch the engineers in the lab who did this experiment. They just go ecstatic when it works, because you never know, those feathers get a little charge on them, electrostatic charge, just like, and that will cause them to stick to things, just like that rubber balloon. Okay, we'll come back over here. So at the Exploratorium, for the 25th anniversary of the moon landing, I built this exhibit. It's called Moonwalk. And it's at that thing that the person is standing on is actually a hexagonal cross section, and each one of these wooden walls here leans in. So the top, it leans in 1/6 of the way. And I have a pendulum here going to the roof of the Exploratorium, which is lined up. It's suspended from a point in the center of this large cylinder. And so the force of gravity, the component of the force of gravity pulling the person into the surface is 1/6 G. So I call it the Moonwalk exhibit. And you could turn sideways in your sling and walk around the 36-foot circumference of this moonwalk and find out what it was like to walk on the moon. This was a really fun exhibit. We actually had 2 of these suspended platforms, and on the moon you can jump. You can jump way high. If on the Earth you can jump 3 feet, then on the moon you can jump 18 feet. And we had explainers with 2 of these reenacting scenes from Chinese kung fu movies where they'd both jump 18 feet in the air and try to kick each other and then slam down into the surface. Or sometimes they would leap up and do a flip over the other explainer's head. So, yeah, so basketball on the moon, boy, you know, it's just going to take so long. The ball's going to come down so slow. It's going to slow down the game, I think. Yeah, and so in fact, some organisms on the Earth move quickly by hopping with both feet, rabbits and kangaroos. And it turns out on the moon, the most efficient way for astronauts to get around with the weight on the moon is by hopping with both feet. Not the usual walking gait we use at 1 gravity on the Earth. So I also built a quick version of this device, a small version, where you make an inclined plane. This one I made for walking on Mars, so it has a slope. The horizontal slope in is 0.4 times the vertical distance, and the cord goes to a point on the ceiling which is makes the cord parallel to the surface of this board, and that means that the Earth will pull me in here with 0.38 Gs, and I can feel what it's like to walk on Mars. And then an astronomer I think in the Netherlands, actually, who was working on the Mercury probe, and the Mercury at the acceleration of gravity is also 0.38 g. He had seen my online postings, and so he built one of his own, emulating the gravity on Mercury. So that's so great with things like the ScienceCircle, where you spread the things you do to the world, and later on, someone comes back and shows you something great they did. Okay, so I have to tell you, I'm really proud of this. I have a superpower, and it's the same superpower as Iron Man. It's a superpower you can get. It's called physics. And I really liked it that Tony Stark here on his ring has an MIT ring. And I have one of those too. So that just makes me happy. All right. So with that MIT ring, I can do the escape speed. And we're finally going to get back to black holes in a minute. This is the classic equation for kinetic energy, 1/2 mv squared. And this is the gravitational potential energy around a point or a sphere. The distance r from a sphere, the universal gravitational constant times the mass of the sphere times the mass of the object divided by r. And we can solve this equation for escape velocity. What velocity do I have to have so my kinetic energy is enough to carry me to infinity away from this gravitating thing? And when I solve it, I get this equation. That's a square root. And for the Earth, you have to go 11.2 kilometers a second at the surface, and you can go to infinite distance. From the Moon, it's only 2.3 kilometers per second. It works in reverse. If you drop something from infinitely far, this is the speed at which they hit radius r. So this 11.2 kilometers per second is right in the mid-range of the speed that meteorites can strike the upper atmosphere at. So 11 kilometers a second, 1001, and it's gone 11 kilometers. I mean, we're really moving here. Yeah, and so in fact, in answer to Barragan's question, the orbital speed is a little bit slower than the escape speed. For that, you use the force laws. You set the force that it takes to hold a mass m in an object in a circular orbit of radius r equal to the gravity force. We know that from before. And you solve for the orbit speed. And when you do the orbit speed on the Earth, it's less than the escape speed. It's 7.8 kilometers per second. It turns out it's you divide by the square root of 2. All right. The Moon, the orbit speed is 1.6 kilometers a second. So you can't throw a rock that fast. But one of the fastest rifles on Earth is the Swift rifle. And it launches a projectile at 1.2 kilometers per second. So if we could make a slightly higher muzzle velocity rifle, you should be able to stand on the Moon and shoot a bullet and hit yourself in the back of the head. Yeah. So Barragan, Barragan wonders if meteor strikes kicking up debris on the Moon would have lots of little satellites around it. Well, there's a little known aspect of orbital mechanics, and that is that if you launch something from a point into an orbit, it will always come back to that point in its orbit. So if you launch something from the surface of the Moon, within one orbit, it will strike the Moon again. So it's really hard to launch things into orbit with a single explosion from the surface. So that just never happens, but it was a great idea. So thinking about such things, here's Comet 67P, and all the equations I've been giving you are for gravity of a point or a sphere, and this thing is definitely not a sphere. And so when I found out the mass and the distances to different points on the surface of this comet, using my superpower, I could actually calculate the acceleration of gravity on the surface of the comet. And it's 0.00001 times the acceleration of gravity. It'll fall 1 meter in 2 minutes. The escape speed is 1 mile an hour, or 1.6 kilometers per hour. If you jump with enough energy on the surface of this comet, if the energy would take you 1 centimeter high on the Earth, that would be escape velocity from Comet 67P. That's just amazing. Um, so actually, in front of me here, I'm going to take a break from the slides again. We'll get back to this. Over here, I have a ball, this red ball, and when I touch the red ball, it's going to jump into the air, and then it's going to fall as it would fall on comet 67P. So it jumped up a meter, and it's actually falling right now. If I dropped a ball out of my hand on comet 67P, this is its rate of fall. It's accelerating down, and it's going to take about 2 minutes before it actually hits the surface again. So, I really love to build things in Second Life. And so it was really fun to build a ball that would reproduce the fall rate on, and if you come to the Exploratorium Science Museum in Second Life, Exploratorium Sim, we have an exhibit that has balls that drop at the correct rate for every planet in the solar system. But I haven't put this one in there. But look, you can actually see it's moving now. This is the essence of acceleration. Even though it's accelerating slowly, it's accelerating. Its speed is building up continuously all the way. The one exhibit I had built that had gravity, normal gravity fall, is the one over here that's labeled cat fall. And when I touch it, it'll throw me in the air above it a meter. And then I use the cat technique to fall right side up. So let me touch that again. You'll see I go up a meter, I twist just like a cat and come down. So that's the fall on the Earth, much faster than the fall of this ball on Comet 67P. Churyumov-Gerasimenko to its well-named associates. Okay. And over here, let's see what this one does. Yeah, and so this blue pad over here, if you touch it, it drops a ball with supposed to be the acceleration of gravity on the moon. There it comes. I like how the balls just stick. They must be like anti-super balls. You click it and they drop. Plunk. Oh well. So it's great. One of the great things about Second Life is you can make teaching tools you could never make in the real world. By the way, the balls are programmed to vanish after a minute. They're temporary items, so that I'm a good inhabitant of Second Life. I don't litter the landscape. Oh yeah. So it turns out even though that's a small comet, it's a huge number of metric tons. So a person jumping off of it is not going to affect it measurably at all. So it's still a big chunk of rock. And thanks to the ScienceCircle for decorating the sky with all these wonderful chunks of rock. Sort of makes me nervous standing under them. Okay, but so back in the 1800s, good old Laplace said, hey, wait a minute. If I use Newton's laws and I calculate the escape velocity, I get this equation for the escape velocity. What if I put down the escape velocity as the speed of light? What does this mean? So you put in c here. Oops, sorry, I hit my microphone. So what does it mean if I put the speed of light in? What does it take to get an escape velocity that's the speed of light? So we got this equation. If the radius of the object is 2 times its mass in kilograms times the universal gravitational constant divided by the speed of light squared, that would give you an object that light could never escape from. And when you do that calculation, you find that an object that has the mass of the sun, the radius, if you could pack the mass of the sun into a radius of 3 kilometers, light could not escape. And this is just such a weird object. It eventually became known as a black hole. Well, you shouldn't use Newton's equations with the forces and at this level. So in 1915, Einstein wrote down the equations for general relativity, and de Sitter found the solution for the escape velocity and solved it. And the most amazing thing happened. He got the same equation. The equation you get by simply solving Newton's laws is the equation you get by solving Einstein's equation. This is the radius. So if you have the mass of the sun in a radius of 3 kilometers, it becomes was eventually named a black hole, where nothing can escape that event horizon. Just an amazing object. This is something called a gravity well. This is one at the Exploratorium. It's a surface of plastic that has a shape it's a hyperboloid of revolution. It's the height is -1 over the radius, and that gives you an inward force on this bowling ball. It's being pushed in with an inverse square force law. So you can investigate gravity. If you put your hand on the inside of this bowling ball and try to find the force outward you have to exert to keep it from falling into the hole, the force goes up mightily as this gets steeper and steeper towards the center of the hole. And this is the standard thing you see when they draw black holes. They call it the curvature of space-time. And this is the standard thing. And what this is actually showing you, and that from this point to this point, the distance along the surface is the distance between those 2 points. And so from here to here in a straight line, the distance is actually the greater distance on the curved surface. So this is actually showing you the warp in space-time. Gravity changes the vacuum. Gravity changes the distance in a vacuum, and I'll give you a quick lesson on that in a minute. So the sun has this weak, it deflects space a little bit, and we've actually measured that. A neutron star has the mass of the sun in the size of a city. It might be 10 kilometers, 15 kilometers in radius, much bigger than a black hole. And it curves the space near it quite a bit more strongly. Yes, good old Homer Simpson. I love that. And a black hole, this curvature actually at the event horizon does go vertical. So in answer to Charlize's question earlier, the curvature of space-time has a discontinuity at the surface of a black hole. A discontinuity that you may say means that an infinite force would not make you escape. Even light itself cannot escape from the black hole. And of course, when searching for this online for images, I found this wonderful image of the person in the bathtub pulling the plug and seeing the curvature of water time. The thing about the black hole is that, you normally say it's not the fall that kills you, it's the sudden stop. Well, it turns out for the black hole, it's the fall that kills you. You can be in free fall towards the black hole and it will kill you. And the reason is that if over to the right over here, there's a black hole and here's an object falling in, the point on the object that's near the black hole has a bigger red force than the point on the far side. It has a smaller force. And a point in the middle has an in-between force. It's the force shown by the little purple arrow below. So when we look at the relative force on the near side and the far side compared to the middle, the object is stretched along a line towards the black hole. This is the tidal force. And so anything falling into a black hole feels this, as you start to fall in, you feel this gentle stretch building up. And in fact, the Earth falls towards the moon. The moon is pulling on the Earth. We fall towards the moon. The near side of the Earth falls more, has a bigger force on it. A rock on the near side has a bigger force than a rock in the middle, which has a bigger force than the rock on the far side. The Earth falling as a whole, this pulls up 2 tides. The near side pulls towards the moon as the Earth falls to the moon, and the rear side is left behind. The other interesting thing is the objects fall towards the moon. This pulls them in. At the poles, they get pulled in. So you don't notice this, but at the poles of the Earth, the tides pull down the surface of the Earth. Ooh, untidy. I like that. Okay. Um, but now let's remove all this talk about Earths and moons and black holes and look at a person. So in Neil deGrasse Tyson's book, Death by Black Hole, he points this out. If you're falling feet first into a black hole, your feet are pulled towards the black hole more strongly than your head. And that causes, at first, you just feel this gentle, wonderful stretching. But as you get closer, the stretching builds up. By the way, you're also, the edges around your circumference are also pulled in. So it's a gravitational corset which pulls you in. Ah, the ring is made of black hole matter. Oh, wow. Okay. Um, oops, sorry. That, so how strong is this tidal stretching as you fall into the black hole? So here, I wanted to get a picture of a 1 meter long steel rod, and here's a 1 meter long steel rod. And if this were to fall into a black hole at 300 kilometers above a 10 solar mass black hole, and that has a event horizon radius of 30 kilometers, the steel rod would be ripped to shreds. All right. So yeah, that's it. It's just if you want to help with your figure, the black hole is a good way to go temporarily. Um, but the this just think of that. 300 kilometers above a black hole, a steel object. The tidal force is strong enough to rip apart a steel object in free fall. You don't have a chance. Yeah, those negative sizes. Okay, so a little bit. That's a little bit about black holes. There's far more about that. Um, let me continue to a different sort of black hole. So if you go out in a night sky, um, you might see the Milky Way, and you're seeing stars and gas that glows and dust that's dark. But if you look in the infrared, you can see through the dust. And here is the 2-mass infrared photo of the Milky Way taken from Earth. Looking at this photo, you realize we are in the boondocks. We are not. We are way out on the edge of this galaxy, looking towards the center in there. The infrared lets us look through the dust. So this would be quite the night sky picture. Yeah, it's thin. And this is a close-up of the center of the Milky Way. You can see the 1 light-year bar on the bottom. And these two arrows are pointing to the very center of the Milky Way. And we know at the center of the Milky Way, there is a supermassive black hole. And the supermassive black hole has 4 million times the mass of the sun. Now, every time you add a mass of the sun, the radius goes up by 3 kilometers. So we know that black hole has a radius of 12 million kilometers. But don't worry, it's only 0.000004 of the total mass of the galaxy. It's a big black hole, but it's a tiny fraction of the mass of the galaxy. How do we know that? You can always ask that. And we know that because we have watched stars orbit the center of the galaxy, and there's nothing there that they're orbiting. But to take a star and swing it around in its entire orbit in a couple decades just means there must be a massive object there. And just a few weeks ago, astronomers put together something called the Event Horizon Telescope, using radio telescopes covering the entire surface of the Earth. And that telescope has a resolution that will allow them to resolve the supermassive black hole's event horizon. We'll get a chance to see it in a year or two when they process the data. There's a lot of data to process. The thing they're looking at, if it were on the moon, it would be the size of an orange. And so it takes a really high resolution telescope to show you the size of an orange on the moon. And that takes this telescope the size of the Earth. And they did it. They did it. They took the data, and maybe we'll get a real picture. All the event horizons of black holes you've ever seen have been drawn. They're artist conceptions, but they're actually going to get the picture. Yeah. And indeed, Barragon's correct. Um, when you fall through the event horizon of a black hole, or at least your atoms do once you've been ripped to shreds, there's no coming back. It's a one-way passage into it. And information travels at the speed of light, and it can't get out either. So when you fall into the black hole, um, you will know what's in there, but you'll never be able to tell your friends. And that's the essence of hell for a teacher. We teachers like to share, and not being able to share what you discovered. You're the only one who knows what's inside a black hole, and you can't share it. That's just evil. Okay, so here's the thing I promised you about space. So consider taking 4 space stations in deep space and making them in a square. The square is the same distance between all 4 objects, all 4 right angles. Right. Well, it turns out the giant black holes, the supermassive black holes, because they're so big, the tides get weaker. The tidal force gets smaller, like the inverse 6th power, inverse cube of the distance. And that inverse cube means you can actually fall through the event horizon of a supermassive black hole and survive. So if you're going to fall into a black hole, pick a supermassive one. By the way, some supermassive black holes have 10 billion, as in 1,000 million solar masses. And when they're that big, the density of the material inside is less than the density of air on the Earth. So, it's very strange things out there. And we're sure they're there because we watch their effect on other galaxies. So now what I'm going to do is I'm going to move 2 stars, perhaps neutron stars, to either side of the middle of one of the lines in this square. We haven't moved the space stations at all. Now, if you measure the length from one of these space stations to the other, the distance on a straight line between them is now greater, because the presence of mass, putting these 2 masses on either side, warps space. It puts more distance there than there was before. And yet, when you look at the light, or whatever you're sending back and forth to measure the distance, it's traveling in exactly the same straight line you saw. It's just there's more distance there. We've actually done this experiment. It's a little more complicated. The red thing here is, this planet here this is Earth's orbit around the sun, and this is Mars's orbit around the sun. And we've put a spacecraft on Mars, and we send a radio signal from the Earth to Mars, and then the spacecraft sends it back to the Earth. So we can measure, using the speed of light, the distance from the Earth to Mars. And we know, because we know Mars' orbit, we know the distance we should get for the answer between the Earth and Mars. But when the signal goes near the sun, there's more there. The mass of the sun puts extra distance into the vacuum of space. And we've done the experiment, and it's really there. A mass, the presence of mass. Yeah. And in fact, an object out here in space, this is a galaxy, can bend the image of another galaxy in the distance around. So even though you hear that light has 0 rest mass, well, yeah, but light never is at rest. So light has mass. E equals mc squared. Light has energy. Light has mass. And light bends under gravity. And here's an image that shows that. This distant galaxy has been bent into what's called an Einstein ring by the gravity of the nearer by galaxy. And sometimes there's matter. But by studying the bending of light, we can measure how much mass there is there. And when we do that, we find that there's lots of mass in the universe we cannot see. It's invisible mass. It's been given the misleading name of dark matter. And it seems to be 83% of the mass of the universe. And so that's just crazy. Yeah, I like that. You have to feel the matter. So if you have, here's what's going on here. Here we are on the Earth looking out into space. Here's a galaxy. Here's a distant galaxy. The light from that distant galaxy marches towards the Earth. It's spreading out in straight lines, but then it gets near this galaxy and its gravity bends it so it comes to the Earth. And we believe that light travels in straight lines. So we think that the light has traveled from over here. So we see this distant galaxy. We see it located over here. Kind of strange. Oh yeah, some good talks. I do this with a wine glass. I actually melt the bottom off of a wine glass and hold it up between my eye and a distant green light. And there's only one green light over there, and yet this particular wine glass is bending the light using refraction, not gravity, to give me these other green images. And by placing it just right, I can even get that Einstein ring. Oh, yes, but actually, you probably shouldn't use a torch to melt a wine glass after you've drunk the wine. And so when we look at stars orbiting galaxies, the orbit tells us how much mass there is in the galaxy, and this curve, lower curve here, is what we'd expect if all the mass was visible, and the upper curve shows the actual rotation rate, revolution rate of these stars. So it tells us that there's mass in there that we cannot see, and this is the discovery image for dark matter. All right. But in addition to all this, this whole thing about the distortion of distances in space, there's Einstein in his original equations for general relativity, he knew that the universe was expanding. Oh no, he thought the universe was static, and he knew that gravity should make the universe collapse. So he reasoned there must be a repulsive force that holds the universe out against the attraction of gravity. So he put a term in his equations that was the repulsive force to hold the universe static. And then Hubble discovered that the universe was expanding. And Einstein took the term out and said it was his worst mistake. But recently we discovered that the universe is accelerating its expansion. So scientists put the term back in, the cosmological constant. And so it was Einstein's double mistake. He took it out and he should have left it in. And that tells us that 74% of the energy in the universe is this mysterious substance that has gravitational repulsion, dark energy. I'll just give you a few more slides here. I'm going to go a little bit over. I apologize. So the Earth rotates, and it bulges a bit at the equator, 0.3%. Greatly exaggerated on the left over here. It's such a small bulge, you can't even see it. So what do you mean by the surface of the Earth? Well, there are three different surfaces of the Earth I'm going to talk about. There's something called the ellipsoid, where we draw a smooth ellipse in the cross-section of the Earth and just average it all out. There's the actual surface, which is the black line. We call that the topographic map. And then there's a thing called the geoid. And the geoid, it matches the surface of the ocean when it's ocean. But what you have to do is make a canal through the mountains of the Earth. And the water level of the oceans in that canal is the shape of the geoid. So three different surfaces: the real surface, the mathematical surface, average, and the water level surface. And essentially this mean ocean surface, this geoid, can be a reference level. Yeah, that's right. A great, yeah. So Bong, thank you, Bong. Yeah, that's Brilliant Blunders. A really, really good book. So yeah, imagine the problem with this rock up here on Comet 67P. It's got to figure out which way down is. And here's this horribly complicated object. And it's doing this integral of being pulled in all directions by every bit of mass. And look at these rocks just sitting up here on the surface of the comet. They figured out which way down is, and they didn't do any math. Well, on the Earth's surface, there are places with stronger gravity in red and places with weaker gravity in blue. And it turns out there are some places in the ocean where over a few hundred kilometers, the elevation of the surface of the ocean compared to the ellipsoid is different by 80 meters, 100 meters. So you think of the ocean as this ultimate level surface going around the surface of the Earth. But if there are places where there are extra dense rocks under the surface of the ocean, it pulls the ocean down into a pit. And where the rocks are less dense, the ocean bulges up. So in order to measure the actual shape of the Earth, we put a satellite in orbit, LAGEOS. It's a brass ball. It weighs 400 kilograms. It's 60 centimeters in diameter and has 426 laser corner reflectors on it. It's just a dumb ball of brass. And I actually, just to give you an example of it, over here on the side, I actually have a 60 centimeter sphere. So I'm going to raise it up so you can see it moving up and down. So that's LAGEOS. But the Italians decided they would go one better and make a better one. So they built one out of tungsten. And this tungsten ball over here, right next to it, Larry's, here's the tungsten ball, has the same mass, but it's only 36 centimeters. And so it turns out it has more mass and less air resistance. Now you have to realize these are orbiting at the height of the ISS, the International Space Station. They're 300 miles up, and there's not much air up there, but they wanted them not to be slowed down by the air. They wanted them in free fall. So that's why they made them. And in my next image, I will actually show you. So a 36 centimeter diameter, is Larry's. And it's a tungsten ball with retroreflectors. And they were able to precisely measure. Yeah, when they come down, man, watch out. They're going to make it to the surface. This let them precisely measure the shape of the Earth. And then in 2002, we launched the GRACE satellites, 2 satellites, and they're 140 miles apart when they orbit the Earth, a couple hundred kilometers, 220 kilometers apart. And they orbit the Earth. And between them, there's a microwave beam that lets them measure the distance apart between these satellites to within a tenth the width of a human hair, 10 micrometers. And that distance, that precise distance measuring, allows them to really find the exact shape of the Earth. And this is so sensitive that they could use it to watch the disappearing water under California during our drought. So in 2002, when they launched the satellites, they measured the gravity of California. And then in 2008, the gravity had decreased, drawn in red in this diagram. And by 2014, and they can measure a 2 centimeter change in the thickness of water under the surface of the ground. And so they watched the water level under the ground of California go down by tens of meters. And the amazing thing was, farmers are supposed to report how much water they pumped from the ground. And guess what? They lie. We actually now can use gravity eyes to look under the ground and watch the water go away. And we can measure a couple of centimeters of water with the GRACE satellites orbiting overhead. So I think I'll actually stop there. And I'm sorry I went over, but yes, they lie. So I'll stop there and say thank you, and I'll take questions. Oh, wow, good audience. Lots of friends out there. Nice to see you all. Oh, yeah. Oh, sorry. I will do one more thing. I put it in the back here, and I really have to show you. So, all right. I have to do one more thing here. I have to bring forward. This is a model that I designed and my friend Gitana built of a gravitational wave. So we found out that mass can distort space. And so what you're seeing here is a gravitational wave moving through space. And the distance in space changes top to bottom and right to left. I'm going to actually rotate this for a minute. There we go. So you get it at an angle. And you can see from this gravity wave that it stretches space vertically and compresses it horizontally, and then does the opposite. So when this arrives at Earth, it changed the distance between the mirrors in an interferometer called at the Laser Interferometric Gravitational Wave Observatory where I work. So this was made in Second Life. It's a really nice three-dimensional animated version of a gravitational wave. And I just had to show you that. And also, it's very much Second Life. This is the sexiest gravitational wave animation I've ever seen. Right, and so I asked my colleagues at LIGO what would be the effect of this gravitational wave on you if you were very close to its combining black hole source? And they said, well, the gravity waves would be the least of your worries. The tidal forces varying will rip you to shreds. But they thought that the human ear would be able to directly detect the change due to the gravitational waves. Yeah, so Katana, I apologize. I went a little bit long there, and I almost forgot to show your gravitational wave. And it's a tour de force. Trying to make an animated three-dimensional sculpture that works at this speed in Second Life is quite the challenge. So Gitana out there in the audience thought about it for a while and actually succeeded. I was so happy. I just wrote the equations. Yeah. Okay, any questions out there? Yeah, as the director of the SPLO and the Exploratorium Science Museums, I come up with ideas that I'm not good enough to build in Second Life. I can build some simple things, but when I can challenge an expert programmer like Katana or Emily Starbrook, then I know I've come up with quite the idea. Oh yeah, so there's a great set of articles about is really general relativity the answer, because we can't seem to bring together general relativity and quantum mechanics. And so there's a book, oh drat, was it by Merman? No, there's a physics book out there looking at alternates to general relativity, and loop quantum gravity is one of them, and also special relativity is another one. So scientists are always coming up with new ideas, and it has to explain everything that we've observed that is explained by general relativity and do something better. Yeah. Oh, Ravelli. Okay, thanks, Naka. Oops. Let's see if I had I'll give a picture here of LIGO. This is the Laser Interferometric Gravitational Wave Observatory. And these two arms, these multiple kilometer long arms, the distance between the mirrors is changed by the passing gravitational wave, and it causes light to change in the interferometer. So it turns out when you do a giant project like the LIGO interferometer, you're required, in the old days, you're required by the National Science Foundation to do education in addition to it. And what LIGO did to provide their education was they hired the Exploratorium in real life. In fact, my department at the Exploratorium, to come help them do their education. And so I get to go there a couple times a year and actually visit the interferometer at LIGO, Livingston, Louisiana. And I get to ask questions of the physicists there, and that's really great. So yeah, I suspect, I predict that gravitons exist, but they're so difficult to detect, I don't know if they'll ever be detected in my lifetime. Um, oh yeah, so in fact, with two gravity wave observatories, one in in Hanford, Washington, and one in Livingston, Louisiana, we can make sure we've detected gravitational waves. They confirm each other, but we can't tell where they came from. But as soon as we get a gravitational wave detector in Italy, which is coming, Germany, Japan, Australia, India, then it'll be like a telescope, and we will be able to look at the place they came from and see what's there. Yeah, it's at the Hanford Reservation with all of its radioactive waste. So I haven't. They're going to build an education center there too, but I haven't been invited yet. Yeah, so there's another spacecraft called LISA, which is a gravity wave detector in space, and they just launched successfully a test subject called LISA Pathfinder, and they're going to measure the distances between satellites. Put up 3 satellites and measure the distances between them, and using interferometry. And then when a gravity wave comes by, it will make a signal. But they can make the distances between the satellites greater than those at LIGO, which makes it a little more sensitive. And they're not disturbed by earthquakes and winds and vibrations of trees falling in the forest, which actually does disturb LIGO. And so they'll be able to go to lower frequencies and see a whole new category of objects. That's right. The sensitivity is amazing. Right. So in fact, what a great question by Mademoiselle. Um, the if how can if nothing can escape a black hole, how can we see gravitational waves from them? Well, it turns out that as the two black holes orbit each other, and there's a nice video in my box. If you touch the Gravity Movies note card giver and look at there's a movie there showing two black holes orbiting each other and colliding. So the black holes, gravity from the black hole does extend out beyond the black hole. Gravity does make it out of the black hole, but not ripples in gravity. But the gravity that extends out of the black hole beyond the event horizon, as the black hole sweeps around, it distorts the space outside the black hole, and that makes an origin. So the gravitational waves have their origin outside the black hole, so they don't have to come out of the event horizon. Yeah. So yeah, so the static gravity that comes out of an object doesn't carry information. If you wiggle the gravity, um, you can make it into a wave, and we know waves carry information, music, images. Um, but if you wiggle an object inside the black hole, the waves don't get out of it because gravity waves travel at the speed of light. But if you wiggle the space around a black hole by moving the black hole side to side, that wave starts out outside the black hole and it can travel. So really good question. Um, yeah. So for example, there's 2 ways to look at light. If you take an electric charge on the end of a wand and you wiggle it back and forth, um, electromagnetic waves radiate out from that positive charge being accelerated back and forth. But if you build a detector for the electromagnetic waves and you make it sensitive enough, those electromagnetic waves will arrive in a quantized form. It's an all or nothing detection. So we say that those electromagnetic waves are quantized, and the quantum is the photon. So you can have these photons of light that are quantized. And the quantization of the gravitational wave would be called the graviton. But it has such low energy. It is, although we've done some amazing detections. So I won't say it's totally impossible, but nobody's done it yet. So no gravitons yet. So another interesting thing was we knew that black holes existed because when gas around the black hole orbiting it close to the black hole collides with other gas around the black hole, it gives out X-rays. So from the X-ray emission, we know that there's a whole family of black holes in the range of 10 solar masses. We know that there are supermassive black holes at the centers of galaxies. We watch stars orbiting them for our own, and they also give out X-rays. But we didn't know about black holes in the mass range of 30, 40, 60 solar masses. And the very first thing we discovered from LIGO is a 20 and a 30 solar mass black hole coming together to make like a 40 plus solar mass black hole. So we discovered, not only did we discover gravitational waves, at the same time we discovered a whole new category of black holes that we don't know how they're made. Yeah, so in fact, I have another lecture I give in which I plot the equation of mass versus radius, a mass radius diagram. And on there, there's a line which is where an object turns into a black hole, and there's a line where an object turns into a wave. And where the two cross, you get a quantum black hole, which is 10 to the minus eighth kilograms. So there's some really interesting possible particles out there, and it's so far out from things we've ever detected that it's definitely going to be a surprise if it's ever detected, and certainly have some surprising properties. Well, I've gone well over, so I'll give you all a break. Thank you so much for hanging in there with me, starting out with Galileo and Newton, and going to the International Space Station, and all the way to LIGO and gravitational waves and black holes. And off in the background here, you actually see the model of a black hole with the accretion disk around it, underneath the space shuttle and the astronaut in free fall. And I hope you enjoyed. Yeah. Yeah, I'm glad that people hung around. It was a great audience. Thank you all so much for coming and being attentive. I think we'll probably leave these objects out here. I think some of them you can copy, not the gravitational wave, but some of the others. By all means, pick up the movies and take a look at those in your spare time. Oh yeah, great. Thanks for the landmark, the Exploratorium. You at the welcome, there'll be 4 pillars around the welcome area, and they'll take you to wonderful exhibitions in the sky. In fact, one of the exhibitions we have in the sky is a reenactment of the Big Bang, which I didn't do gravitationally yet, but there's lots of interesting stuff centered around the Big Bang. Yeah, Exploratorium group is still active. I run the Exploratorium in Second Life. Um, in a year, I'm retiring from the Exploratorium, and I haven't found someone to take over running it in Second Life. I'm really working at that. Hopefully, I can find someone to at the museum to run it. Oh yeah. So in fact, null subset burner, Hawking radiation, great stuff, and that is something for another day. I even in the extended lecture, which I didn't get to, I didn't get to Hawking radiation. Hawking radiation is so it turns out the rule is that nothing can cross the event horizon, but it turns out there's a thing called tunneling, where an object disappears at one point in space and reappears at another, never having crossed the space in between. And so it's possible for things to tunnel out of a black hole and radiate away. But in that tunneling process, we lose some of the information. So, yeah, very interesting. There's lots more. It's so amazing that this old simple force of gravity has so much in it. Okay, I'm going to head off. Thank you all for being attentive. Play with my toys. That's right.